Electromagnetism, FETE 121, Study Unit 3, Northwest University. This unit covers the magnetic phenomenon and some calculations. The phenomenon. This is a coil wounded by copper wire and an iron bar for a core. As soon as a current is passed through it, it will display magnetic properties at the opposite ends, in this case attracting iron nails. Here are just a few of the applications of magnetic principles: induction coils, loudspeakers, generators, meters, and of course transformers. Current generation by means of a coil rotating through a permanent magnetic field. Slip rings carry over the induced current from the conductor loop to the output. The coil goes through different phases of the cycle, creating a sine wave. At the starting point of the cycle, in other words 0 degrees, we have maximum output because it cuts the magnetic field at a right angle of 90 degrees. At 90 degrees we have no conductors cutting through the magnetic field. Therefore we have no output in volts, in other words 0 volts. At 180 degrees the conductors are again at 90 degrees with reference to the magnetic field, but now moving in the opposite direction, which causes the voltage sine wave to go negative. Therefore, maximum negative voltage. At 270 degrees, we again have the conductors cutting through none of the magnetic field lines, therefore again giving a 0 output. When it returns to the start, in other words 360 degrees, we will have maximum output again in the positive direction because it is again also cutting through at 90 degree angles to the magnetic field. Factors governing electromagnetism. First of all, we need a current flowing through a conductor. With the conductor having windings expressed in N, number of turns, it will of course strengthen the magnetic induction. Then also we have the length of the magnetic field indicated by the small letter L. All this will then determine the value of the EMF, in other words also expressed as Fm. Current in a conductor and iron filings experiment. Try this at home and see what happens. Using a 9 volt battery and a fair piece or length of copper wire going through a square piece of paper with iron filings on it, current flowing through the conductor will cause a magnetic field as indicated according to Fleming's right-hand rule. Coiling the conductor produces a stronger magnetic field of force. Left and right-hand rule of electromagnetism. The right-hand rule, illustrated at the left, simply shows how a current-carrying wire generates a magnetic field. The thumb shows the direction of the current and the fingers curling shows the direction of the magnetic field. The left-hand rule shows what happens when charged particles, such as electrons in a current, enter a magnetic field. You need to contort your hand in an unusual position sometimes for this rule, and it is illustrated below. The thumb indicates the direction of force, in other words movement. The index finger points in the direction of the magnetic field, and the middle finger points in the direction of the current flow. Let's have a look at Ørsted's law quickly. In 1820, a Danish physicist, Hans Christian Ørsted, discovered that there was a relationship between electricity and magnetism. By setting up a compass through a wire carrying an electric current, Ørsted showed that moving electrons can create a magnetic field. What is a magneto motor force? The symbol used for MMF is FM and is measured in ampere. The value of the MMF is directly proportional to the product of current and the number of windings. Therefore, FM equals I, which is the current, times N, the number of turns, measured in amperes per turn. Do the following calculation. A coil of 110 windings carries a current of 200 milliamperes. What is the MMF generated? Stop the presentation quickly and work it out for yourself. Answer is 22 amps per turn. What is the magnetic field strength? The magnetic field strength is directly proportional to the MMF and inversely proportional to the length of the magnetic field. Determining the value of the magnetic field strength. It is indicated by the letter H and is equal to Fm or MMF over the length of the magnetic field. In other words, N times I over L. Now do the following calculation. A coil with 200 turns carries a current of 3 ampere in a magnetic field length of 11 centimeters. What is the field strength? Stop the presentation now and work out the answer for yourself. The answer is 5454.5 amperes per meter. This is the end of study unit 3 on electromagnetism. Check eFundi for the first online test, which will follow soon.